video, I would like to share you the oxidizing behavior of KMnO4 in organic compounds. Okay, so KMnO4, as you know, alkaline KMnO4 is a strong oxidizing agent. It will reduce, you have studied that it will oxidize alcohols to aldehyde than to carboxylic acid. So it's a strong oxidizing agent. You cannot stop at the aldehyde stage. So we'll see what are the other applications of KMnO4 in this regard. So in this KMnO4, the manganese in +7 oxidation state. So the reactivity of KMnO4 mainly depends upon in which condition it is employed, that is acidic condition, neutral condition or basic conditions. So in acidic condition, Mn+7 will be converted into Mn+2. In basic and neutral conditions, it will be reduced to, +7 is reduced to Mn4. In that state, it will be like KMnO2. Okay, so first we will see the oxidation of aromatic side chains. So that any side chain, alkyl side chain attached to benzene ring will be oxidized by KMnO4 to corresponding carboxylic acid. So how this is happening? Let us take toluene. The equation for this reaction is toluene plus 2 KMnO4, and in presence of alkali and heat conditions, you will be getting potassium salt of carboxylic acid plus 2 MnO2 plus water plus KO. So this is the reaction that is happening. So here you can see +7 is reduced to manganese 4, and this toluene is oxidized to carboxylic acid. Now you will be, as defined this, you will be getting the corresponding carboxylic acid. If you are taking isopropyl benzene, so that means CH, CH3. No matter how many carbons are attached to the alkyl side chain, this will be readily oxidized to benzoic acid. But if you are having a tertiary butyl group, means CH3, CH3, like this. If you are performing this oxidation, KMnO4, OH- under heat reflux conditions, this side chain will not be oxidized by KMnO4. The reason is that this side chain, you know, this is the benzylic carbon. The carbon, alpha carbon attached to benzene is called benzylic carbon. The benzylic carbon is not having any alpha hydrogen in it. Okay, so in other cases, here you have alpha hydrogen, these 3 alpha hydrogens are there. So you have to understand that the alpha hydrogen atom in the alpha position, that is benzylic position, is susceptible for the attack of oxidizing agent. So there must be at least one such alpha hydrogen in the benzylic position in order for this reaction to happen. So this reagent, starting material which does not have alpha hydrogen will not undergo side chain oxidation. Now we will see the substituted. What is the role of KMnO4 on substituted alkyl benzene? So here you have chlorine at the beta position. No matter what is the substituent attached to it, you have to see only the alkyl side chain is having alpha hydrogen or not. So here there are 3 alpha hydrogens, so it will be readily oxidized to beta-chlorobenzoic acid. Okay. Now here this is xylene. Okay, 2 methyl groups. So this is at ortho position. So orthoxylene. So both the alkyl side chains will be oxidized. So we will be getting dicarboxylic acid, 1,2-dicarboxylic acid. Now if you have 3 such groups, okay, 3 such groups, all 3 alkyl side chains will be, alkyl groups will be oxidized to corresponding tricarboxylic acid. You know, the benzene ring is resistant to oxidation under this condition, alkaline KMnO4. Okay, this will not undergo oxidation under these conditions. But if you have a fused heterocyclic ring system attached to benzene ring, This is a pyridine ring attached to benzene ring. Okay. So heterocyclic system, if it is fused with the benzene ring, this ring will be oxidized. Okay. So you will be getting this position. Okay. This position will be oxidized. The ring will be oxidized. So you will be getting CO2H, CO2H. Okay. Similarly here also, this is phenolene, this is isophenolene. Same conditions you will be getting here isophenolene, nitrogen over here, CO2H, CO2H. So this acid is known as phenolenic acid. This is called cingamaronic acid. Okay. So you have to remember that benzene ring will not undergo, if it is alone, it will not undergo oxidation under these conditions. But if it is fused to any heterocyclic ring system, that will be that benzene ring will be oxidized to corresponding carboxylic acid. Two such examples are written over here. Application of use of alkaline KMnO4 oxidation is in the synthesis of saccharin. So for that you will be taking sulfonamide with orthoposition CH3 group. So if you are doing the oxidation over here, this CH3 will be oxidized to carboxylic acid. So you will be getting S double bond O, NH2, then C double bond O, OH. So this carboxylic acid will be getting. Now these are in proximity, minus H2O will be eliminated. So this is such, H2O will be going. So you will be getting saccharin. S double bond O, NH, C double bond O. So this is called saccharin. So this is the application of using alkaline KMnO4 oxidation. So next application of alkaline KMnO4 oxidation is the oxidation of aldehydes and ketones. So under basic condition, this aldehyde, KMnO4 and alkali will be reacting, and you will be getting corresponding carboxylic acid and MnO2 plus water. So one example is any aldehydes, aromatic aldehydes will be oxidized to corresponding carboxylic acid. This is porphyral CHO will be oxidized to carboxylic acid. So this can also happen in acidic medium. Acidic medium that you have studied in plus 2 classes, C6H13CHO, KMnO4, and acid we will be using H2SO4. Then you will be getting corresponding, the CHO will be oxidized to C6H13 CO2H. Okay, so the mechanism will be the RC double bond OH. Now if you are adding acid into it, what will happen? This oxygen is having lone pair into it. So this lone pair will be attached to the acidic proton. So one lone pair is lost, so positive charge will be coming. Okay. So in the next step, that MnO4 minus will be attacking MnO4 minus. So now this carbon will be electron deficient because this will have tendency to go there. So this O minus will be attacking here. This will be going like this. So you will be getting RCHOH. Okay. Then OMnO3 in this manner. Now what will happen? Again water molecule will be coming, and this will be since this carbon is attached to metal containing reagent, this is electropositive in nature, so this can readily take up this proton. This will be going in this manner, okay, and this bond will be clean in this manner. So you will be getting what? RC double bond OH. So this portion now becomes carboxylic acid, okay, plus MnO3 minus, and this is becoming H3O plus. So this is how that reaction is happening. Third application is oxidation of alcohols. So alkaline KMnO4 and barium permanganate selectively oxidizes alcohols in a multifunctional compound. So this molecule contains ester as well as OH group. So this is a secondary alcohol. So this will be oxidized to corresponding ketone. Secondary alcohols will be oxidized to ketone. Ester is acid. Okay. Next is this is an alkyne. This position is called propargyl carbon. This is a propargylic alcohol. Propargylic primary alcohol, you can say. And here there is an OH group. Okay, that is protected by tributyl silane, OTBS protection. Okay, silyl group reagent which is used to protect the OH group. So this unprotected propargylic alcohol will be oxidized to corresponding. This is remember, this is not used in strong acidic or strong basic conditions. Okay, so this is a mild condition employed, sodium dihydrogen sodium phosphate. So in that case, controlled oxidation will be happening. So you will be getting here, instead of carboxylic acid, you will be getting aldehyde. Okay, so that is the thing you have to remember. Fourth oxidation is oxidation of amines. Amines will be oxidized to corresponding nitrobromide. So alkaline KMnO4 oxidize tertiary amines. So tertiary amines means this carbon R. So fifth is the oxidation of nitro compounds to corresponding carbonyl compound. So this is a nitroalkane. The nitroalkane will be oxidized to corresponding aldehyde. So this is attached to primary carbon. This is attached to secondary carbon. So this will be oxidized to ketone. Okay. Now let us see how this is happening. Mechanism. We will see. So RCH and double bond O minus. So this is the nitroalkane. So as you know, these two hydrogens are highly acidic in nature because it is attached to nitro group. So highly electron withdrawing group. So this OH minus readily pick up one acidic hydrogen. So the bonded pair will be shifted to here like this. So you will be getting RCH double bond N. Here nitrogen is having positive charge because nitrogen's valency is exceeding 3. So here again positive charge O minus plus H2O. Okay. Now this reacts with MnO4 minus. MnO4 minus. So what will be happening? That MnO4 minus, O minus will be attacking here. Okay. And CH N O minus positive charge O manganese double bond O minus. So this type of cyclic manganese ester will be formed. Let us see how this is happening. Now this is like an eno, right? So this will be coming over here. This pi bond will be attacking this oxygen. That bonded pair will be converting into lone pair into manganese, so that manganese plus 7 oxidation state will be reduced to plus 5. Then this will be oxidizing here. So you will be getting RCHO Mn double bond O minus in this way. Okay. Now let us see. This is getting oxidized. Okay. This portion has to be converted into aldehydes. For that, this has to shift over here, so that RCHO will be coming over here. Okay. This will be shifted to here, and this will be coming back to here. Okay. So the remaining things how we will write? We will write it as RCHO plus one oxygen is lost from manganese. So this will be Mn double bond O minus. So MnO3 minus plus this NO2 minus will be going, NO2 minus. So this is how this nitro group will be oxidized to aldehyde group. Next is a very important application of potassium permanganate in basic conditions, which is that alkanes will be converted into 1,2-diols, that too cis 1,2-diols. Okay, stereospecifically cis 1,2-diols are formed in this reaction. So let us take an example of cyclohexene. It will be oxidized to 1,2-diols in first and second position. OH group will be coming. So it will be either at the both the beta phase or both the alpha phase. Either ways it can happen. Now let us see the mechanism of this reaction. So this is alkene and this is our MnO4 minus. It will be in +7 oxidation state. Here you can also write MnO4K plus, that is understood. Okay. So now what is happening? So as you know, manganese is electropositive metal. It will have vacant d orbitals into it. So this pi bond will be attacking oxygen. This electron pair will be shifted to manganese and this will be attacking over here. Okay, or you can start from this side. This pi bond will be attacking our alkene carbon. This will be shifting here and this pi bond will be going as a lone pair into the Mn's d orbital. So you can write the cyclic manganese ester. Cyclic manganese ester. This is cyclohexane ring. So you can write in order to show it is happening in the same phase, you can show the beta bonds, manganese, okay, O minus, double bond O. Now the oxidation state of manganese, since accepts 2 electrons, this will be in +5 oxidation state. Okay. So this is a cyclic ester intermediate. Okay. Now this will be undergoing alkaline hydrolysis. So this will be cleaved. So this is like HOH. This will be cleaved in this manner. So you will be getting OH plus and then OH and then OH O minus double bond O. This is how this reaction is happening. So remember the formation of cyclic ester, then cleavage. So this is happening at the same phase. So you will be getting both cis alcohols. Next time I would like to introduce you a reagent in which KMnO4 is used along with sodium periodate, NaIO4. So this is used as a mixture, sodium periodate and KMnO4. So where KMnO4 is also employed for the oxidation. So I would like to introduce to you in this context, because KMnO4, I was discussing about KMnO4 oxidation. So this reagent is having a common name and it's called Lemix von Rudolph reagent or simply Lemix reagent. Okay, so you have to remember this is used for the oxidation of alkenes and sodium periodate and KMnO4. Mixture is used. So let me introduce a structure in which two functionalities are there. There is OH group and double bond. Okay, so as you know, KMnO4 will be oxidizing both alcohol will be oxidized to carbonyl, and the alkenes also will be oxidized. Okay, we are seeing this formation of cis hydroxylation, 1,2-diols. Okay, so but if you are using Lemix reagent, what will happen? This will be doing oxidative cleavage of the double bond. Okay, not neither hydroxylation nor conversion to carbonyl compounds. This will be cleaving this pi bond, and you will be getting the product. So this will be one carbon. So that will be like osmosis. This will be the end carbon will be oxidized to CO2H without affecting the OH group. The other one will be oxidized to ketone like osmosis. So that is the importance of Lemix reagent. Okay, so you have to remember this one. Alkenes, if you are seeing KMnO4, you should not write 1,2-diol. So you have sodium periodate along with this. So this is the role of Lemix reagent, oxidative cleavage of double bond. So that's all about KMnO4.